Hello everyone. So in this tutorial, I will be explaining you how to do the setup portion for NACA 0012 airfoil. So in the last video, we have created the meshing. So in this case, we will do the setup. So just double click on setup. So make sure your double precision is on so that the Ansys Fluent will consider more number of digits after the decimal point when you turn on the double precision. And you can select this number of solver processes based on your system. So my system has 4, so that's why I'm going with 4. If you have 2, you can go with 2. If you want, you can go with 1 also. That's fine. And then click on start. So again, you can see the status on the bottom left corner. It is saying starting Fluent. It means my Fluent is getting started. So let's wait for it. Okay. So now you can see our mesh has been loaded and our setup portion has been started. So as we know in setup portion, there are a lot of options. So I'm not gonna cover each and everything because it will make the video very lengthy. So I will just cover the options which you have to focus on and which you will be using if you are doing simulations for NACA 0012 or any airfoil 2D simulation. So first thing which I would recommend you doing is you have to always check the perform your you have to always do check your mesh, and you have to check the quality of your mesh. If something is not right with your mesh, you can see using these statistics which are showing in the console, and then you will get to know that what is wrong in your mesh. Then you can go back to meshing, you can redo the meshing, and then you can come back. Because if you run your simulation using a wrong mesh or very poor mesh, then again you won't be getting the desired result, and then you will be getting frustrated why I'm not getting results and all. So it's better to always check the mesh and evaluate the quality of your mesh. So moving ahead, the first option in setup is general. So since we are doing incompressible simulation, so I'm going with pressure based solver, and I'm doing a steady state simulation. If you want, you can, if you're doing transient, you have to make sure you have to select transient. And in my case, the gravity doesn't play that much significant role, so I'm not activating the gravity. So that's all in general, pressure based solver and steady solver. Now coming to models, so you can see we have different models. If you have multi-phase means when you have, let's say, liquid as well as, let's say, vapor. In those kind of situations, you have to turn on multi-phase. We don't have anything like that. Energy you will turn on when you are doing something related to thermodynamics. We don't have that. So likewise, we have radiation, heat transfer, species, and all other options as well. So for this tutorial, the only important thing for us is viscous. So double click on viscous. So by default, it is selected as K omega, but for external aerodynamics, Spalatalmas is a better turbulence model as compared to K epsilon and K omega. Again, it depends on other factors as well. So I will recommend you to test for different turbulence models. I have ran simulations for different turbulence models in my case, and I get to know that Spalatalmas performed best for me. That's why I'm going with Spalatalmas. And I will keep all these model constants, all these numbers to be by default. So click on OK. After this, you have to go to materials. So make sure you have air in your fluid, and then you have to make sure what density or viscosity you want to keep. So in my case, based on the Mach number and Reynolds number, I did some calculations to compute my inlet velocity, viscosity, and all those stuff. So I found my viscosity to be 1.0634. So I will keep this. Again, depending on your Mach number and Reynolds number, you have to figure out what is your inlet velocity, viscosity, density, and then you have to enter those values. Don't just copy paste the numbers which I'm showing in this tutorial. Coming to cell zone condition, make sure your fluid domain is fluid, which we did in design modeler. If you remember, if you forget to do it there, you can change it to fluid here as well. So everything is correct here. Then go to boundary conditions. So this is the important thing. So make sure the airfoil boundary is a wall type. And in that wall type, make sure you have no slip boundary condition on, and your boundary should be stationary. So you can see my wall is stationary and I have no slip boundary condition. So if you remember your uh, fluid dynamics course which you took in your undergrad, so no slip boundary condition means the velocity of the fluid at the boundary of airfoil will be zero. So apply close. So same goes with airfoil top surface as well. Type should be wall. And we have to make sure our wall is stationary and no slip boundary condition. So stationary and no slip. Okay. Again, don't play around with this roughness height and roughness constant if you don't have any idea about it. But if you have some values, I would recommend change it according to your requirement. Coming to domain, so domain means this green area which you can see here. So it is an interior. We don't have anything in this to change. So leave it as it is. Next is inlet. So make sure your inlet should be velocity type. If it is of something else like pressure inlet or far field, you can select that option based on what it is. So in my case, I'm going with velocity inlet. Click on edit, and make sure your velocity specification method is magnitude and direction. Because in NACA, in airfoil simulations, we usually do simulations for different angles of attack like 0, 10, 15, 20, 18, and so on. So in that case, make sure it's better to go with magnitude and direction. So keep reference frame as absolute. Again, enter your inlet velocity. So in my case, it is 52.0408,348. Again, how I got this number with the based on my Mach number and Reynolds number. So gauge pressure, initial gauge pressure should be 0. And for this tutorial, I will be simulating for 0-degree angle of attack. But if you have any other angle of attack, so let's say 10-degree angle of attack. So here you will enter the value of cos 10, and here you will be entering the value of sin 10. If you don't want to enter the value, you can click here, click on expression, and just type cos 10. So it will automatically take the values of cos 10 degree. Okay. So in our case, we don't have all these things. We just have 0 degree angle of attack, so I know the value for cos 0 is 1 and the value of sine 0 is 0. But if it is 10 degree, I would have entered cos 10 value and sine 10 value. And coming to this intensity and length scale, so I will keep the turbulence intensity to be 0 and length scale to be 0.01. Although since I have kept the turbulence intensity as 0, length scale doesn't matter, but still. Again, these numbers depends on, you have to play around with this number to see what is the optimal turbulence length scale and intensity for your case. There will be nothing to change in interior domain. Coming to outlet, so make sure your outlet is pressure outlet and click on edit, and make sure your gauge pressure is 0. And here also you can keep these things as it is. No need to change it. Click on apply and then close it. So that's it for the boundary conditions. Then we'll go to reference values. So I want to calculate each and everything from inlet. So let me make this thing a little bit bigger. So I will click on this arrow and click on compute from inlet, and you can see it automatically took the velocity and viscosity value which I wanted. Then nothing to do with reference values, name expression, method control. Let's go to report definition. So while simulating, I want to keep an eye on the drag coefficient and lift coefficient for the airfoil. So drag coefficient. So where I want to measure drag coefficient on both airfoil top and bottom surface. So again, right now I'm simulating for 0 degree angle of attack. So that's why I have kept x equal to 1, y equal to 0. But if you are simulating for, let's say, 10 degree of angle of attack, here you will put the value of cos 10 and here you will put the value of sin 10. I want to print the value for coefficient of drag and lift in console. Click on OK. Same, I want to measure the lift coefficient also. So lift coefficient. Then make sure this you have selected lift coefficient here. I want to measure lift coefficient for both surface, print to console. So again, y is 1, x 0. But if you are simulating, let's say 10 degree, here you will enter cos 10 and here minus sin 10. Don't forget minus sign. Okay. So that's it. If you want to, let's say, print or measure something else, you can create report for that as well. Now go to monitor, click on residual. So I don't want to converge the solution based on these residuals. I will monitor the residuals by myself while running the simulation, and once I see that the residuals are converged, I will stop my app by simulation by myself. But if you want, you can change this uh, convergence criteria and keep the numbers whatever you feel is good for your simulation. Then no need to change anything for cell register and all those things. Cell register basically we use whenever we want to do mesh adapt. We want to refine the mesh using mesh adaptation. So maybe I will talk about how to do that in another video, not for this one. So let's not look at that option now. Next, go to initialization. So there are two types of initialization, hybrid and standard. So if you click on standard, you need to give the initial value for pressure, velocities and all. So in my case, I don't have all these numbers. So I will just click on hybrid initialization. So what Ansys Fluent will do in this case is Ansys Fluent will, based on all my setup and all, Ansys Fluent will come up with some initial value of pressure and velocity, and then based on that, it will assign the number. So remember, by initializing, if you guess the value which is very close to your actual result, your simulation will get converged very quickly. You can see our initialization has been done. Next, I will click on run calculation. So since it is a steady state, so I have to just mention the number of iterations. If it would have been, let's say, transient, then you have to mention how many time step you want, what should be the size of time step, and all those things, which is not uh, we have to worry about here because we are running steady state simulation. So let's say I want to run, let's say 500 simulation, then click on calculate. So you can see now my calculation says Ansys is calculating each and everything. So you can see I'm getting this plot for lift, drag, and residual. So I can monitor all these three plots and then I can see when it is getting converged. And once it is getting converged, I can stop my simulation. Also, one more thing, once you are done with this simulation, make sure you write the case and data file. So how to do that? You have to just click on file. So right now I won't able to click it because I'm running the simulation. But when you click on file, you will see one option of write. In that write option, you will see one option case and data. So make sure you write that case and data file and save it wherever you want so that later if you want to, let's say, plot results and all, you can read those case and data file and you can plot the contours. So that's all for this video. See you in the next time. Thank you.